So let's have a look at the content for alcohols, alkyl halides and ethers. So firstly, let's have a look at alcohols. So alcohols is when you have a carbon chain and you have an oxygen that's bonded to a hydrogen. So we've talked about alcohols in the past when we did nomenclature, but we haven't talked about the reactivity. So this is just a little bit of a refresher about what an alcohol is and how we name alcohols, this first section. So hydrocarbons, remember, are compounds that contain only carbon and hydrogen. That's where the name comes from, hydrocarbon. If you have a hydrocarbon with one or more hydroxyl group, so an OH is a hydroxyl group, then that is called an alcohol. So the hydroxyl can be a primary, secondary or tertiary. So a primary alcohol is when you have a alpha carbon, so a carbon that's bonded to a OH, so a hydroxyl, and it has another carbon chain coming off it. This is a primary alcohol. A secondary one is when you have two carbon chains coming off the alpha carbon, and a tertiary is where you have three carbon chains coming off the alpha carbon. So this is our primary, secondary and tertiary alcohols. So you've probably come across primary, secondary and tertiary before. We might have been talking about amines, or we could have been talking about carbocations. So it's quite common terminology, and the principle is the same when we're talking about it. Okay, so alcohols, as we all know, they are very important for industry as well as for our biological activity. Examples of each could include ethanol production, which is a product of fermentation. So remember, fermentation is your anaerobic respiration. So only some microorganisms can produce ethanol through fermentation, and so a yeast species is an example that I've put up here for you. So another example of an alcohol, we'll look at the structure of cholesterol later, but cholesterol is an example of an alcohol, and that OL on the end of the name indicates that there's an alcohol in that compound. And cholesterol, is essential for the structure of cell membranes. So your cell membranes, to maintain the ideal fluidity, need cholesterol in the bilayers, the lipid bilayers. So key reactions that alcohols undergo is nucleophilic substitution and beta elimination. Okay, so we'll talk about these a little bit later when we go into reactivity. So a quick refresher on what IUPAC naming is. So IUPAC naming is the naming that we're going to be using. A common naming we're going to try and steer away from, but you will find that your textbook has common naming in it. So you might need to get familiar with a few common names in order to follow your textbook. So just a refresher on your number of carbons. So here's the nomenclature here. So for 1 carbon it's meth, 2 carbons it's eth, 3 carbons it's prop, 4 carbons it's bute, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, 10 dec. And we'll only go up to 10 carbons. So the first thing you want to do when you're doing naming is you want to identify the longest continuing chain of carbons, and this is what we call our root name for that compound. Secondly, once you've identified the longest chain, you want to identify any alkyl groups or other groups that are coming off that main chain that aren't included in that carbon count. After you've done that, you want to work out which groups have the highest priority. So remember the priority here. Okay, so the highest priority is your carboxylic acid, your amide, aldehyde, ketone, alcohol, amine, and then you've got your hydrocarbons at the end there. So finding your highest priority, you start numbering so that the the lowest number is on your highest priority group. Okay, and when we're putting the name together, we do it in alphabetical order for the substituents, and that goes out the front. And we'll do some examples again to refresh you on your IUPAC naming. Okay, so naming alcohols. So remember, the nomenclature for an alcohol has an OL ending, so we call them ols. So our most simple alcohol is methanol, so meth being one carbon, AN saying it's an alkane chain, and OL saying it's an alcohol, so methanol. Then we've got ethanol when we've got 2 carbons, and propanol when we have 3. So propanol, when we start having 3 carbons, you can have the hydroxyl coming off the terminal carbon, as in propan-1-ol, or we could have it coming off the central carbon, as in propan-2-ol. So if you have it off the end carbon, you don't necessarily need to write the 1 in there, but they have done for clarity in this textbook. With the second one, you definitely need to say that it's coming from the second carbon. So there's propan-1-ol and propan-2-ol. We get more complicated, we can look at 2-methyl, so 1,2-methyl propan-2-ol, and then we can go into diols, so meth, eth, and alkane chains, 1,2-diol. And we have triols, so the same way. And this is the structure of cholesterol, so you can see there is that hydroxyl group coming off that large molecule. So in chemistry, one of the most important things is polarity and solubility. So a lot of chemistry is based on these fundamental principles. Determining the degree of polarity of a molecule is dependent on the number of polar substituents that are contained within that molecule. So remember, polar substituents are groups that have a large electronegative difference between carbon and hydrogen and the group that you're looking at, so that we get a dipole across that bond. So remember, a dipole is when you have a region that's delta positive and a region that's delta negative, as shown in this picture here. So things that produce dipoles or polar regions within a molecule are atoms that contain nitrogen, oxygen, fluorine, chlorine, bromine, and sulfurs. So looking at your periodic table, we're really going for that right hand side just past carbon. So nitrogen, oxygen, fluorine, sulfur, chlorine, bromine are the main ones you'll come across. The more bonds going to that electronegative atom, the more that atom influences it. So for example, if you have a single bond to an oxygen versus a double bond to an oxygen, the double bonded oxygen is more polar than the single bonded oxygen. And it's all proportional to what you're comparing it with to start with. Okay. So the compound's ability to be soluble in an aqueous environment, so in a water environment, is a factor of hydrogen bond acceptors and hydrogen bond donors. So a refresher on what that is. So looking at this picture here, we have an electronegative oxygen, we've got hydrogens bonded to it, we have a dipole across these bonds, so you can see that's indicated by the delta negative and the delta positive. So this oxygen also is sp3 hybridized and has 2 lone pairs. Those lone pairs can accept a hydrogen bond. Okay, so we can accept a hydrogen bond coming in there, and this hydrogen can donate a hydrogen bond to another water molecule that's close by. Okay, so the presence of the hydroxyl groups make these hydrogen bonds. So the oxygen's delta negative, the hydrogen's delta positive, and then that hydrogen bonds with another oxygen that's delta negative. So really you've got a hydrogen that's torn between 2 oxygens or 2 electronegative groups, and one of them has a covalent bond and one of them has what we call a hydrogen bond. So remember, hydrogen bonds are weaker than covalent bonds, but their interactions are quite strong. So the presence of a hydroxyl group makes alcohols more polar than the corresponding alkanes because of this polarity, this delta negative characteristics, the dipole. So the thing that makes alcohols polar is their ability to hydrogen bond with water. Let's look at some examples of alcohols. So starting at our more simple alcohol is methanol, and as we're increasing our carbon chain, we end up with heptane 1-ol as the largest one. So let's have a look at the solubility. So we've got solubility in water, which is a polar solvent, and we've got solubility in hexane, which is our non-polar solvent. So looking at methanol, it's very soluble in water and not very soluble in hexane. As the chain gets bigger, the ability to be soluble in water decreases. So the heptane 1-ol is very non-soluble in water, so you'd actually get 2 layers forming, whereas it increases its solubility in hexane as the chain gets longer. So solubility of water decreases with increasing alkyl chain length. Okay. So solubility in drug design. So remember, drug design is a major part of chemistry, and a lot of you, although you might not be directly implicated by drug design, the products of drug design may be something that you have to think about later on in your degree or your careers. So for a drug to be effective, it needs to be able to travel through the body to where it needs to act. And in order for this to happen, we need to get the right balance between lipophilicity and hydrophilicity. So lipophilicity, how well it dissolves in lipid conditions, so fatty conditions, and hydrophilicity is the dissolving in an aqueous or water environment. So assuming that so let's look at this example here. So we've got cyclohexane, so purely hydrocarbon compound, no polar regions in it, and comparing that to glucose, which has hydroxyl groups all through it, introducing that polarity. By introducing the OHs, we've increased the polarity of the compound. So we're going from cyclohexane, which is non-soluble in water, to glucose, which we all know is highly soluble in water. The glucose is able to enter your body and travel around to where it needs to go, whereas your cyclohexane can't. So compounds that are too hydrophobic, a possible way of fixing their bioavailability is to make them more polar by adding polar groups on. Obviously, if a compound is designed to fit a specific receptor and you put on polar groups, it may not fit into that receptor. So then you have to look at other ways of delivering the drug to where it needs to go. So alcohols, let's have a look at the basicity of these alcohols. So the ability of a hydroxyl group to accept a proton, so acting as a base, it's accepting a proton, is important in the context of dehydration, so the loss of water, and forming carbocations. So we're going to talk a little bit more about these concepts later on, but this slide is just to introduce you to the idea before we get into the nitty-gritty theory of it with examples. So looking here, we have a carbon with a hydroxyl group coming off it, and we have an acid. So this is going to act as a base, and the lone pair is going to attack the hydrogen's positive charge, and then we're going to get an oxonium ion. So an oxonium ion is a water with a positive charge that's attached to a carbon. So we've got that positive charge on the water. Because it's now an oxonium ion, it's a fantastic leaving group. That water wants to dissociate and become water and get rid of that positive charge. So it produces a dehydration reaction. So we get the dehydration, so we get the water being produced, and we get the carbocation being produced. So remember, back to chemistry for living systems, we talked about carbocations. We talked about carbocations and their stability. So it's the same as we talked about the primary, secondary, tertiary alcohols. So it's the same for the carbocations. So a tertiary carbocation has 3 R groups coming off it, the secondary has 2 R groups coming off it and a hydrogen, and the primary has 1 R group and 2 hydrogens. So the tertiary carbocation, with those large R groups surrounding it, is very stable. So the tertiary carbocation is the most stable. And for a reaction to proceed via a carbocation intermediate, it needs to be a tertiary carbocation intermediate. And again, we'll see this in practice a little bit later on in the lecture. So haloalkanes. So haloalkanes, also known as alkyl halides, so depending on which textbook you'll be looking at, is basically an alkane with a halogen coming off it. Okay, so they could be aliphatic or cyclic. They can have branched, linear, all sorts of different backbone structures, but there's going to be a halogen directly bonded to an sp3 carbon. So a carbon that's making 4 bonds. So we have chlorinated hydrocarbons. So DCM, dichloromethane, we will be using in the laboratory this semester. And chloroform is another example. And chlorinated hydrocarbons are commonly used as solvents. Key reactions that haloalkanes undergo are nucleophilic substitution again and beta elimination. So same sort of chemistry as our alcohols. So one example of your haloalkanes is your CFCs, so chlorinated fluorocarbons. So they are mostly phased out now, but used to be used as refrigerants, solvents and propellants in aerosols. They're odorless, non-toxic and non-corrosive, and they're pretty safe. But when they travel into the environment, they make their way up into the stratosphere unchanged, and then they're hit by UV light and they're broken down into free radicals, which then go on and destroy the ozone layer. So for your curiosity, I put in the initiation and propagation steps. So we've kind of talked about this last semester, so it should hopefully make some sense to you. So we've got our CFC, it's hit by UV light and the chlorine free radical is broken off. And the chlorine free radical then attacks an ozone molecule, and then we have this propagation step, and this is what breaks down our ozone layer in the stratosphere. So naming alkyl halides. So again, looking for the longest continuing carbon chain here, we've got dec. Okay, so it's a decane. How are we going to do our numbers? We could go 1, 2, 3, 4, 5, 6. So we have a 2, 4, 6. Or we could go 2, 3, 4, 5, 7, 9. If I got my calculator out and went 2, 4, 6, what does that number get? And 5, 7, 9, the 2, 4, 6 adds up to a lower value. So that would be the correct way of naming this one. So it'll be 2,6-dichloro, because we have 2 chloros, 4-methyl decane, alphabetically put together, so the chloro comes before the methyl. Again, remember when you're looking at the alphabetical, it doesn't matter if it's di or tri, you look at what the actual group is. So in this case, we're looking at that C for chloro when we're looking at the alphabetical order, not the D. We're looking at the C. So the last functional group that we're going to be looking at today is the ethers. So it's similar to an alcohol, but instead of having this hydrogen, we then have a a carbon containing group. So in this example was CH3. So what does this mean in terms of the chemistry? So they're similar to alcohols, but they're less polar. Okay, so they're less able to interact with water and make hydrogen bonds, and that's due to the steric hindrance, so the bulkiness in a three-dimensional space of that group that's coming off that oxygen. So that's blocking the hydrogen bonding from occurring. This means that the alcohols are more polar and the ethers are less polar, and this also means that the ethers, in terms of polarity, sit more towards an alkane than they do an alcohol. You could talk it in terms of moderate polarity. So the moderate polarity that these ethers have make it a very good solvent. Okay, so examples are tetrahydrofuran that you may eventually come across, or tetrahydropyran. Another example is the 1,4-dioxane. Example of one is a naturally occurring antibiotic, so non-actin. So you can see that here there's lots of ethers. Here's another one in the structure. Okay. And they can be cyclic or acyclic. Okay, so naming ethers. The nomenclature is a little bit harder. It can be quite cumbersome, so we're not going to focus on it, but it would be nice to have an idea of looking at a name and working out if it's an ether, if it's an alcohol, and if you had to draw a simple one, be able to coin a simple one together. So again, we find the longest chain, we add to it the name of the attached alkoxyl group. So we've got 1, 2, 1, 2, so it's ethane, and this is eth-oxy. So we go ethoxy, ethane. Another example, we have meth-ethol, so we've got ethanol, so ethanol. And here we have 2-chloro ethoxy, so 1,2-chloro ethoxy. So it'll be 2-chloro ethoxy ethanol. And the last one here is the cyclopentane, and then we have the propoxy that's derived from the propanol, so 1, 2, 3. So you're probably wondering what side gets the alkoxy group and which one doesn't. So the one that's the bigger or the more important group, the higher priority one, gets the normal nomenclature, and the smaller of the two gets the alkoxy nomenclature. So you can see here, ethanol, it's got the alcohol, higher priority, that becomes ethanol, and the other one gets the alkoxy. Here they're the same, so it doesn't matter which way you do it. And here, cyclopent, so we've got 5 versus 3, so this is the higher priority, and this is the lower priority. So let's look at reactivity. So before we get into the actual reactions, we want to look at why these reactions are occurring. And there's 2 main reasons why things occur. So leaving groups and the solvents. So let's have a look at the leaving groups to start with. So it's quite a busy slide, but if you can bear with me, I'll try and talk you through it. So first of all, what is a leaving group? So a leaving group is a group that's leaving a molecule and being replaced by something else. So in this example, we've got a nucleophile coming in, and we've got the leaving group leaving, okay? So here it's a neutral leaving group, so it gets a negative charge because it's picked up these 2 electrons from this bond onto it. If this is a positive charged species, for example, the oxonium ion, so remember a water with a positive charge, then when it leaves, it picks up an extra 2 electrons and becomes water neutral. Okay, so whenever you have something leaving, it picks up 1 negative charge. So if you're a positive, it becomes neutral. If you're a neutral, it becomes negative. So good leaving groups are weak bases, and the weaker they are, the better. So the best types of leaving groups are conjugate bases of strong acids. So remember, the conjugate base is the part that's left over when the hydrogen is lost. Okay, so for example, if we have hydrochloric acid, its conjugate base is the chloride ion. Okay, so the stronger the acid, the weaker the conjugate base, and the weaker the conjugate base, the better the leaving group. So you can see here, the strong acids make really good leaving groups. Their conjugate bases do. So we've got iodine, bromine, chlorine are good leaving groups. And that's got to do with the pKa. So the smaller the pKa, thinking back to your acids and bases, that means the smaller the pKa, the stronger the acid, the weaker the conjugate base. So here's a table here just for easy memory. So you've got your iodine is the best leaving group, water, bromine, chlorine, and then you've got your bases, actual bases that aren't very good at leaving. Okay, so the order is the opposite to basicity. Again, looking at these halogens, so as you're going down your halogens, you're increasing the size, the basicity is decreasing, and the nucleophilicity is increasing. So as you go down, you're getting a better, a weaker base, so it's a better leaving group. So let's have a look at our solvent effect. So the two different types of solvents are protic solvents and aprotic solvents. So protic solvents are solvents that have hydrogen atoms that are bound to oxygens or nitrogens. So water is a protic solvent, methanol is a protic solvent, it has a hydrogen bonded to an oxygen again, and formamide is another one, so we've got nitrogens bonded to hydrogens. So we've got these hydrogens that can come away quite easily. So protic solvents, okay, so why is the solvent important? So solvation weakens a nucleophile. So if particularly a nucleophile is in solution, it may be in a solvent which can go around that nucleophile and kind of trap it in a shell kind of environment, if you can think of it like that, and it makes that nucleophile unable to do what it needs to do. So nucleophiles are negatively charged. Okay, so if they're in an environment where there's lots of positive protons around or positive molecules around, that's going to solvate that nucleophile and make it unable to do its job. So in a protic solvent, the nucleophile can get solvated. So the size of that nucleophile is also important. So the smaller the nucleophile, the more tightly it can be solvated. If the nucleophile is large, it's less tightly solvated. So on the opposite, a aprotic solvent is a solvent that lacks the ability to solvate. So examples include acetone, acetonitrile, and DMF. So let's have a look at reactions and their different solvent types. So if we have so what have we got? We've got an iodine nucleophile coming in and attacking a carbon, and then we're having the bromine leaving. So we've got a substitution, we're swapping the bromine to an iodine. A substitution reaction in methanol, so it's a protic solvent. That protic solvent is going to encapsulate this iodine I- with a solvation shell and make that iodine less available to come in and act as a nucleophile. So we would say this one would be a fairly slow reaction. If we have an aprotic solvent such as acetone, we're looking at the structure of acetone, there is no hydrogen that's bonded to an electronegative oxygen or nitrogen, so it's aprotic. This iodine will not be affected in any way by the solvent, and it can readily come in, attack, and kick out the bromine. So under these conditions, it's been found that this one's actually 500 times faster. So when you're looking at reactions, the solvent is a very, very crucial player in your reaction. Okay, so let's have a look at the key concept reactions. So hydrogenation, alkoxide formation, substitution SN1, SN2, elimination E1 and E2, and ether cleavage. So these are the main ones that we're going to be going through. So let's firstly have a look at hydrogenation. So hopefully this is familiar from Chemistry for Living Systems. So hydrogenation is achieved using the reagent hydrogen on a palladium catalyst. So hydrogen is the gas that you bubble through the reaction, or you surround your reaction in a hydrogen atmosphere, and palladium is put into the actual reaction vessel. So hydrogenation is the hydration of unsaturated hydrocarbons. So remember, unsaturated hydrocarbons are hydrocarbons that don't have a full amount of hydrogens per every carbon. So an example of a saturated hydrocarbon is your alkanes. So every carbon has 4 bonds, and they're either a carbon or a hydrogen. So unsaturated means that there are double or triple bonds present in the molecule, so not the maximum amount of hydrogens that it can have. So an example here, we've got a double bond. We've done it with palladium and in a hydrogen atmosphere, and we've added 2 hydrogen atoms across it. So for every equivalence of hydrogen that you put in there, you can quench 1 double bond. So if you have a triple bond, you're going to need to put twice the amount of hydrogen gas, and palladium is the catalyst, so that probably wouldn't change much. And it pushes it across to make the double bond, and then from the double bond to the single bond. So alkoxide formation. So alkoxide formation occurs when an alcohol is reacted with alkali metals. Okay, so alkali metals being sodium or potassium. So for example, if you have a alcohol of some sort and you have a potassium metal that you've put in with the alcohol, you would form the alcohol alkoxide. So the potassium alkoxide, because you've got the potassium here. So you would form the potassium alkoxide, and hydrogen gas would be produced. So it's similar to the same way that you would make sodium hydroxide. So water with sodium makes sodium hydroxide and hydrogen gas. So the nomenclature of the alkoxide is derived from the alcohol. So I've done this example here for you. So ethanol with the sodium solid will make you eth, so eth oxide, and it's a sodium counterion, so you'd call it sodium ethoxide. So let's have a look now at SN1 and SN2 nucleophilic substitution reactions. So nucleophilic substitution occurs by two major pathways. It can be SN1 or SN2. So they've got different mechanisms at which the reaction proceeds. So the SN stands for substitution of a nucleophile. So regardless of the mechanism, the same thing occurs. So let's have a look generally at our structure. So we've got a nucleophile. It can be neutral or negatively charged, depending on which one you're using. It comes in, so the lone pair of electrons attacks an R group, so a carbon of some sort, and attaches. And then the lone pair of the electrons on that bond there go onto the leaving group that you've got. And then obviously if it doesn't have a charge, picking up those two extra electrons would give it a negatively charged leaving group. Okay. So here, if you have a nucleophile that's neutral, it will adopt a positive charge because it's donating two electrons away, so it's going to be changing to a positive. So SN1 nucleophilic substitution reaction. So SN1 has one intermediate stage, and that's the carbocation that's produced. So SN1 reactions occur when you have a tertiary alcohol or haloalkane, and first of all you would have your leaving group leave and form a carbocation. So if you have an alcohol, you would have the protonation of the alcohol to make the positive carbocation of water. Okay, so we've looked at this one already. Okay, and then when that bond breaks, it quenches the positive charge, so it's a favorable reaction, and you'll get this positively charged carbon floating around. And then the bromine comes in and attacks that carbon, and you'll get the bromine addition. Okay, so what we can see here is that we've got a tertiary alcohol, we've got the leaving group leaving, we've got a carbocation being produced, and then we have the second group coming in. So in this case it's the bromine attacking the carbocation. So because we have a carbocation being formed, we've got a carbon with a positive charge. When that bromine comes in, it can come in from any face of the molecule. So there's lots of room, it can come in from any angle, and what we find is we have a mixture of the stereochemistry. So hopefully you remember back to R and S. So remember R and S, so when you do the priorities around your chiral carbon, your number in 1, 2, 3, 4, 4 is always in the background, and if it's clockwise it's R, if it's anti-clockwise it's S. So in this reaction here we would get 50% R and 50% S as our products. Okay, so SN2 nucleophilic substitution reactions. So this is when you have a transition state and you have two groups in that transition state. So looking here, we now don't have a tertiary carbon. We have a carbon that has a little bit more room around it. So we've got a secondary carbon here. We have the hydroxyl group coming in. Okay, so it's coming in from one side, and then the bromine is being pushed out at the same time. So we get what we call a transition state. So we've got a partial bond to the hydroxide and a partial bond to the bromine, and because one's coming in from the back side and pushing it out from the front side, we're going to have an inversion of that stereochemistry. So if you started with an S, you're going to end with an R. If you start with an R, you're going to end with an S. So you can see here with our product that bromine has left and we just have the hydroxyl group now added, so we have an alcohol as our product. So we get an inversion of stereochemistry. We have a starting compound that's not tertiary, so secondary or primary is fine for that one. We need a good leaving group, so that bromine needs to be a good leaving group for that one to happen. Okay. So let's have a look at this in a different way. So SN2, looking at the reactivity here, so the more available that carbon is, the faster the reaction is going to occur and the more likely the reaction is to occur. So if we have a carbon that's a tertiary, it's not going to react very fast, if at all. Secondary reacts faster. Primary is going to react really well, and if it's just got no R groups, then it's going to react very, very fast. So looking here, we've got the group coming in to this side of the molecule. So you can see here there's a carbon with 3 hydrogens coming off it, and we've got an X group coming off it, and we've got a nucleophile coming in. They come in close together and make this kind of planar structure, and then this bond here is going to start breaking and this one will be getting stronger, and we will get an inversion of that stereochemistry. So the new group will be on the other side of that molecule. Okay, so that's our substitution reactions. Now, elimination reactions are the next ones we're going to look at. So haloalkanes undergo elimination under basic conditions.